case. Maybe somebody else may want to just check it out. Okay. All right. So you have 50-gram object connected to a spring with force constants 35 Newton per meter, oscillates with amplitudes given 4 centimeter, frictionless, horizontal. What is the total energy of the system? And there will be like a bunch of questions following up. Okay, so this is good. So let's practice this one right there. So what you have, okay, let me draw. Just okay. Sketch here. You have a spring, you have a mass M on the floor like that. And you can say the mass is 50 grams. So it's 5, you can say 50 times 10 to the negative 3 kilogram. The K, the force constant over here is 35 Newton per meter. Okay. Very good. The amplitude is given to be 0.04. I put everything in SI system here. Okay. So now, what is the total the total energy, total energy of the system? So imagine this. Of course, when you want to set this mass in motion, which is going to be in oscillation here, you have to pull it to the maximum displacement, which is the amplitude, right? So at that moment, so what you get over here is at x equal to amplitude. That would be the point where you have 100% elastic potential energy. Does that make sense? Because at that moment, you don't have any velocity of the mass. It's purely just from the spring that is being stretched. So that means over there, you can say it's 100% potential energy. So let me put it over here. Okay, let me put PE just to be obvious here. So it's a potential energy and it's 0% kinetic energy, right? So at that point, you say the energy of the system is going to be 1/2 Ka squared. And that's it, guys. That's part A. You're done. And that will be the total energy of the system as well. Okay, and then you can plug in the numbers yourself. All right, now part B. The speed of the object when its position is at 1 centimeter. Okay, so if you want just do things directly from the conservation of energy, what you need to do is this. Because you already started your energy, the total energy is already this value here. So once you set things in oscillations, at any particular point, the combination of the kinetic and potential energy must add up to this value, 1/2 Ka squared. Does that make sense? Right. So from the conservation of energy, it means the total energy at any point must be 1/2 Ka squared no matter what. Cool. All right. So that means if you already at part B, say, is already at the position of 1 centimeter. So that means at that point, your elastic potential energy is going to be 1/2 K 0.01 meters squared. You guys with me here? Okay. And the rest of the energy must be, of course, coming from the kinetic energy, 1/2 mv squared. Okay. And that's it. You can solve for V from here and you're done. Sounds good? Yes. All right. And if you want to refer to the formula, that can be done too. So if you remember back in the slide, we have a formula that try to link between the displacement, the velocity, and the amplitude. And actually, it came from this. So if I rewrite this equation one more time, 1/2 Ka squared equal to 1/2 Kx squared plus 1/2 mv squared, right? And if I really want the expression for the speed, so what I can do is say, all right, 1/2 just disappeared. There's no big deal. So what I can say is V squared is K over M. And I can say it's an A squared minus X squared. You guys with me so far? All right, I just move Kx squared to the other side. I pull a common factor K out, take the M, divided the K, and then I left with just the A squared minus X squared. And then I can just take the square roots of everything. Does this one looks familiar to you? And we already learned from oscillation that the omega is square root k over m all the time. And that is you right there. So that means you got the expression of the omega square a square minus x squared, the exact same expression that we did, that we put in our slide right there. Nice. All right. But at least now, you can actually get to that by just doing conservation of energy, or if you somehow recognize the shortcut that can link the x directly to the v, that can be done too. Cool. Alrighty, keep going. Part C, find the kinetic energy and the potential energy when the position is given at 3 centimeters. So now it's going to be easy now, right? Because now part C is going to be just like you'd redo the whole thing one more time, except you do it at different position. Now it's x equal to 3 centimeters. So you say at 3 centimeters, your potential energy is going to be 1/2 k 0.03 squared. Does that make sense? Okay.
Okay.
And the kinetic energy is now, because they're not asking you to figure out the speed, you just want the kinetic energy. So it's going to be now even simpler. It's going to be 1/2 ka squared. Let me write the expression down for you. Minus 1/2 kx squared. You just get rid of the potential energy. The leftover must be the kinetic energy. And that is 1/2 k. And then you can set the amplitude, which is 0.04 square minus the position there. And that's it. You are done. This is C and D right there.
Okay.
Does this help? I think I kind of like the oscillation problems because it's straightforward. I would say straightforward in the sense that there are not many things sort of like hidden inside anymore, because you are going back to do the mechanics, right? Just like what you did with the Newtonian physics. Like you do sigma f equal to ma, you do the velocity acceleration, you're doing the energy calculation. So that's why everything's kind of like sort of like straightforward here. Okay, does this help? Yes. All right, very good. All right, guys. No problem. Welcome. Actually, now I get some answer. I don't even get the answer. That's a problem. So when I lost that file that I had the numbers, the answers, that's because usually when I do it in together like this in the Q&A, usually I'll stop here. I don't really do numerical calculations. So that doesn't really help. Oh my God. I don't know where did I put that file. I only have the questions. I don't have the answer. Okay. That was just my bad. That was the time that I made this decision to change. All right. Question 4, definitely yes. All right. Well, we have five questions here. Okay. So all right, we just keep going here. That's nice. Give me a second here. All right. Number 4, you have a particle moves with simple harmonic, of course. All right. frequency is given. All right, so let me put homework 4. Oh, it's homework 5, problem 4. Okay, there you go. All right, so we have a particle with the frequency in hertz. So that's what the information you have right there. And the amplitude is also given. So let me convert it into meter. So it's going to be 0.05 meter. Okay, so first good. I got it right. Okay, through what total distance does the particle move during one cycle of its motion? During total distance, all right? So the total distance. So every time that you have an oscillation, so if you imagine if it's like a mass on a spring, for example, you start from the equilibrium point, okay? And then you just have to oscillate, right? You have a mass over here. And then you say you have to go to the right, which is going to take you to the amplitude in the positive sense. And then it's going to have to come back here and eventually move to the left to the other side of this, which is the negative amplitude, and then come back here. This is one complete cycle, right? So what you have, see, through what total distance, they just want to know the travel distance, all right? So that's what you have to just add all those distance together. Yeah, sounds cool. So it means you're going to the right, 1A, come back another A, go to the left another A, and go back to the equilibrium point one more time. So the total is you have to travel 4A. And that is going to be your total distance each cycle that the particle has to move. Okay, cool. So that's part A. That's done. With me? All right, part B. What is the maximum speed? Now you want the speed. And everyone, if you guys remember, the speed is going to be here. Let me put it here. The speed here is going to be 0, right? At the amplitude on both ends. When you are already turning at your turning point, you want to turn things around. The speed has to go to 0. It's just a fraction of time. And then you just flip this direction. Cool. And then the speed is going to be maximum at the equilibrium point. And if you still remember, we did the calculus stuff, we do the differentiation, and it turns out that the maximum speed is omega times the amplitude. So that means part B, your max velocity is going to be just omega times A. But then everyone still remember, omega is 2 pi, the frequency in hertz. The amplitude is already given. And that's it, guys. So you say 2 pi 3 hertz times 0.05. Everything is in the SI system. So your answer will be in meter per second. Cool. Already. All right. Part C, cats. Find the maximum acceleration. All right. So I can overlay on top of that one as well. So what you have for the acceleration, it turns out the acceleration will be the maximum when the force is at the maximum. So what you have is the A max will show up at both ends. That's A max. Because that's the place where the spring is being stretched the most. So that means the force is being applied the maximum. And at the equilibrium point, that is the one that you don't have any spring stretch or compressed anymore. So the A is 0 at the equilibrium point. Does that make sense? All right. So I hope this gives you like a grand, like a summary of the displacement, the velocity, and the acceleration. So on top of that, you said, oh, it doesn't change yet. All right. On top of that, you say the A max, you have to differentiate those, sinusoidal function one more time, and you will drop out that extra omega, if you remember that. Right? It's going to be omega square A. That will be your maximum acceleration. And that is just 2 pi f, the whole thing square, times the A. And that's it, guys. So you take the 2 pi times the 3, the whole thing square, and then you do 0.05. Everything is in the SI system. It's going to be meter per second square. And that's it. You are done.
Okay.
All right. And where in the motion does the maximum acceleration occur? You say at plus and minus amplitude. Okay. Very good. That's kind of fun. Solving problems Saturday morning. Like, okay. So I'm like work out a little bit. Okay. Question. Okay, no problem. Go ahead. Actually, we can just go through all of them, right? There are not a lot of questions that I posted here. I just realized maybe the number of problems a little bit too small for this module. Just all right. I don't know. Sometimes like too much, you guys kind of like okay, you make like it's kind of losing the focus. What type of question will show up? So I try to pick just the one that's gonna be exactly. Well, I wouldn't say exactly, but close to what I'm going to ask in the exam. Okay. All right. Number 5. Okay. So this is done. Actually, if I just write everything down in series like this is already like a almost the full solution, right? That's kind of nice. I can post this one right away, and then everyone have the same uh sort of like written solution over here. Homework 5, question number 5. Here we go. All right. So I have a particle executes simple harmonic motion with an amplitude given 3 centimeter. What position does its speed equal half of its maximum speed? I think I love this one because this one is like, it's kind of short question. You don't have to calculate too much in the sense that, right, it's not like numerical calculations that you just keep punching your calculators. It's sort of like a little bit, it's not too tricky. It's just because the question is very simple, asking like, hey, where during the simple harmonic motion that the speed is half the maximum? And what do you think? All right. If you sort of like, because we have gone through the first 2 problems over here, I think you can answer this one sort of like you get a clue now. Right. So that means you know that, okay, let's take this. The V max now you already saw is omega A. So you just want wherever it is that the velocity is half. So let me call this as V half. Is going to be omega A over 2. And you want to figure out what is the position that gives you this value, omega A over 2. And we have already seen that you have the relationship between the speed and the position, given that the speed can be written as the omega square root A square minus X squared. Cool? No, right? And what you have over here is, hey, I want this to be this. I just want the speed to be I put the subscript here, just say that's a half speed, let's say, right? So you want this to be half of the maximum. So what you have to do is just substitute it in omega A over 2 equal to omega square root A square minus X square. Okay. And actually you can work this one through. You don't need the omega. I can work through this A square over 4 equal to A square minus X square. So that means the X square is just, all right, 3/4 A square. So that means X is just, I mean, you can put positive and negative sign here if you like, root 3 over 2A. And that's it. You are done.
Okay.
All right. So it's going to happen at root 3 over 2 times the amplitude. That will be the position where the speed is half the maximum. Cool. Very nice. Okay. All right. All right. Feel free to ask more questions if you like. But this is good. This is good. All right, very good. Can we see homework 6? Yes, definitely. All right. So any other question? All right. As while we are at homework set 5. So number 1 and 2, you guys seems okay. Yeah, because I think that is a straightforward question asking those. All right. So if this is good, so everyone's those are here good with 5. Okay. All right. So let me pull homework number 6. Here we go. Homework set 6. Okay, so you want question number 4. Okay, definitely. All right, so this one is very close to what we did in class as well, but we had the different configuration. So this is homework 6, question number 4 already. All right, so we have a light string of mass m and length L has its end tied to 2 walls that are separated by the distance d. So I mean the dimension and everything already given. 2 objects each have a mass m are suspended from the string as shown. Okay, so if a wave pulse is to be sent from A to B, how long does it take? Okay, so when you want to say how long does it take, of course you want to know how fast does it move. If you know the speed of the traveling speed, I mean, if you are able to calculate the traveling speed, then you would just take the distance divided by the speed, right? So at least the concept is this: time that it takes is going to be the distance over the speed, right? And the distance you already can see from that going from A to B, that is L over 2. So the only thing that you need to figure out is what is going to be the speed of the wave that gets generated in that string. Okay, so to do that, you can just do the analysis on the force, because another thing that you need is the speed in a string is square root tension over the mass per unit length. Remember this one, yeah? All right, so that means the thing that you need to figure out is what is the tension. And the mass and length, it seems like it's already given here. This one is just mass per length, which is exactly the mass m and the length L. So that's perfect. So actually mu is already known. So that means the only thing that you really need to figure out is what is T, the tension. Cool. All right. So to do that, now you do free body diagram. So you take, let's say you can look at the point A. So let's say at A, you have these strings. Okay, it's a junction over there. And then you can see that, of course, when you're considering a point on a string there, the tension will be pointing outward everywhere, right? So that's what it is. Okay, and what you can see now is this is a T that you want. T that you really want in calculation is T on the right. Okay, however, of course, there will be T over here. Let me call this T prime, because that's got to be a different tension, right? It's not the same string anymore. And of course, down here, it's going to be the mg that pull this mass down. Cool. Already. So what you have over here is now you can just try to figuring things out from it's a equilibrium position of the whole system over here. So what I can do is I can break this T prime into 2 components. All right, it's not drawn in scale here. My bad. All right, the arrow is supposed to be exactly the same because they are supposed to cancel themselves out altogether to 0. But the point is, okay, if I look at this, okay, what can we do? Okay, I need a different color so you won't get confused here. So let's do this. So if you look at the triangle in the top there, right, from that, ooh, so my hand is not steady. Hey, here we go. So if you look at the triangle over there on top, what you get over there is, you know that the string over here is L over 4. Okay. All right. And the distance, it's D on top. So that means the distance that you left over here is going to be D minus L over 2. You guys with me? And then divided by 2. You got this one? Because if you look at the geometry over there, the distance between 2 walls is D. But then the section of the string that you have left, okay, I can actually write it down here if you want. If you get that, here we go. All right, so over here, I have another one there, and I have the wall. Okay, wall here. All right. I hope. Oh, that's not good. All right. I hope, but I mean, that's well. All right. I think you got it. Right. So you try to figure out the distance that is a leftover from the difference between the distance from the wall D and the L over 2. And then you divide it by 2 on each side. So that's why I got that length over there. So if you take that and then you're going to call this theta, then the one that pointing up is going to be T prime cosine theta. And this one is going to be T sine theta, T prime sine theta. All right. And just by considering this point alone, what you are getting is going to be T prime cosine theta must be equal to mg. That's your equation number 1. And T prime sine theta must be equal to that T that you want right there. You can call this equation number 2. And because, of course, you don't care about the T prime, what you can do is I can take the second equation, divide it out by the first equation. You're going to get the tan theta equal to T that you really want over mg. All right. And that allow you to calculate that the tension is the capital Mg tan theta. All right. Tan theta, you can figure it out. It looks bad, but it's there because the tan is going to be opposite over hypotenuse. But I mean, you can figure it out, even though it's going to look pretty ugly looking. But that's what it is. All right. And that's it. So that means you already knew what the tension should be. That means your speed is going to be square root capital M G tan theta over small m over L. I can flip it up MGL tan theta over small m. And the time that it takes is going to be just L over 2 divided by V. And you are done. Sounds good. All right. This one looks, I mean, I know some of you don't like this kind of question because they don't have any numbers for you. They all sort of like stuck in parameters, M, capital M, the theta, the D, the L, but that's how it's done. Okay. Just, I mean, crack each portion of the unknowns and you just try to, you know, get the equation that it eventually give you that the value of that unknown, which is in this case, the main thing that we want to solve for is the tension, right? So is it good? Does this help? All right. So the key points still try to figure out the tension, right? And because everything else, the problem already gave you the information, the mass of the string, the length of the whole string, the distance between walls, the mass that hanging, the capital M, the value of the G, everything is already known. Very good. All right, I think we should do a lot of this. It's kind of fun. Can we see question 6? Yes, definitely. Okay. Already. So you have a loudspeaker. Okay, so let me pull this one up. So I think this is good. All right, so I hope this helped. All right, so homework 6, question number 6. Here we go. All right. So you have loudspeakers is placed between two observers who are 1/10 meter apart. So along the line connecting them, one observer records sound. All right, so let's see. I think I'm going to do horizontal, that. Okay, and you have two speakers. They call speaker number 1 and speaker number 2. And you know the distance apart is 1/10. Now the line along the line connecting them, one observer record a sound level of 60 decibel and the other is 80. How far is the speaker from each observer? Wait, between two observers. Okay. So the speaker must be somewhere. And because the observer number 1 hear the sound of 60 decibel, so it's supposed to be maybe a little bit away from observer number 1. Does that make sense? All right, it's going to be closer to observer number 2 more than observer number 1. All right. Okay, so let's say that's observer right there, just sitting there. Okay, no. Ooh. Okay, here we go. Already. So let's assume that the distance from the first observer is x. So whatever that is, the distance to the second observer is going to be 110 minus x. Cool. Nice. All right, now let me use the subscript 1 and 2 just to distinguish between whatever going on with the observer 1 and 2 respectively. So what I'm going to do is it's going to be beta 1, which is the level, right? They care about the level. It's a decibel. So it's going to be 10 log the intensity that the first observer observed divided by the constant that we use, 10 to the negative 12, the lowest intensity that human can still hear. Same thing happens to the second observer, 10 log I2 over I0. Nice. Okay. And now all you have to do is solve this too, because you already saw it, that the beta 1 is given to be 60. The beta 2 is given to be 80. Okay, so let me write that down. Now, we already said in class that usually when you would like to manipulate logarithmic functions, usually you don't multiply or divide, you either add or subtract. And because now you want to do the comparison, so the subtraction seems to be a good idea. So what you do is I'm going to take, or you can call this equation number 1, you can call this equation number 2, and I take 2 minus 1, right? Because 80 is more. So it's 80 minus 60. All right, on the right-hand side, I can pull a common factor 10. I have the subtraction of 2 logs. I can set the argument and then just the, oh, sorry, 2 first. My bad. There you go. I take 2 over I0 divided by I1 over I0. You guys do follow so far? All right, and of course, I0 can cancel. And now what we can do next is, all right, almost done. What you can see over here is now is the ratio between intensity, which is fine. Let's recap. The intensity by definition is the power per unit area. But because we can assume if there's no particular direction of the sound, we assume that the sound from the speaker is coming from a point source. So it means everything just go out in a spherical form. So you can say it's going to be P over 4 pi R squared. So with that, we already did this one as well. If you want to compare between two intensity, and if you want a ratio, you can just take the ratio of each term. It's going to be P2 over P1 times R1 over R2 squared. You guys follows this one? You just take two value of the intensity and take the quotient, take the ratio between them. And because in this one, sounds came from the same speaker. So you don't have to have any different value of the power. So they are coming from the same speaker. So the power is exactly the same. So that means now you can substitute R1 over R2 square for that I2 over I1. And that's what you have to do here. So on the left is 20. On the right is 10 log. And now I can do R1 over R2, the whole thing square. With me, guys? So far, so good. All right, almost done. All right, I can cancel that. So this is 2 log this ratio. I can just do the inverse log, which is doing the exponents base 10. So I say it's going to be 10 to the second. It's going to be R1 over R2, the whole thing square. Or same thing, it means R equal to, 10 equal to R1 over R2. Nice. Okay. Am I doing things correctly here? Is my number 1 and number 2 is correctly described here? Yeah, I think so. I hope so. All right. We'll see. All right. Okay. So now with that, R1 is just X. R2 is 110 minus X. And that's it. You will be able to figure out what should be the value of X, and you are done.
Okay.
All right. So X supposed to be bigger than I mean, it's supposed to be big because the ratio is 10. So if you solve that one, can you solve it? Yeah, I think that's pretty good. How did we get 10 to, oh, okay. Over here, okay, let me put on a quick note over here. So over here is like 2 equal to log X. So let's, oh, don't use X. Okay, let's log something. So over here means you can say 10 square is equal to Z. Does this make sense to you? Because whenever you see log over here, it means it's a log base 10. So when you want to inverse the logarithmic function, what do? You do the exponential. But because you're doing exponential with base 10, so you can think of it like you take the 10 and raise to the whole thing. It's like 10 to the whole thing is equal to 10 to the whole thing over here. Okay. And by having 10 exponential with the log, which is the inverse, so you get back the Z. Yes. Okay. Very good. All right. And I think this number looks good, I think. Is it? Maybe, maybe not. 11. 100. Okay, that's pretty good. It's 100. So X is 100. So it's 110. Very good. Meter. Very nice. Done.
Okay.
Very good. All right. Feel free to ask more questions there. All right. Be right back. 1 second. Okay. Any further questions? Yes. Yes. Question 10. Yeah. All right. This set of problem is kind of long because it's about sound in comparison to oscillation, because oscillation is just like kind of like introduction to things. Okay. So let's take a look at that. Number 10. Oh, okay. All right. This is a good one, except that, well, don't worry that in the exam, I don't think I'm gonna have this kind of question shows up because it's really, really physics stuff. Yeah. Okay, so it's a homework 6, question 10. Here we go. All right. So what we have over here is you have a tuning fork. Okay, is giving off the frequency 512 hertz, falls from rest. and it's a free fall. So it's accelerated down with a 9.8 meter per second square. How far below the point of release is the tuning fork when waves of the frequency? This is lower. The reason is lower because, of course, the tuning fork is being dropped, so it's moving away from you, from the observer. So everyone know when the source moving away, the frequency observed will be lower. So reaches the release point. The speed of sound is given to be 340. All right. So the concept of this one is going to be pretty all right in the sense that now you drop tuning fork, and that tuning fork just give off the sound of 512 hertz. So it's going to traveling downward over here. So that is going to be the speed of the source. See, I just put the S in there. That is the speed of the source. And of course, you on top, and of course, you are stationary. So I can say that the speed of observer is 0. You're not moving anywhere. Okay. And the speed of sound is given to be 340 meter per second, which is fine. Okay. So what you really want to calculate is using the Doppler effect, saying that this is the frequency from the source. So this is F sub S. That's the source frequency, 512. But what you really have over here is the observed frequency is lower, and it's 485 hertz. Okay, so it seems like the information is already here in the sense that you should be able to figure out the speed of the source at the moment that you will hear the sound of 485 hertz. You just want to know this sound generated when. When means they're asking how far below the release point. So you want to know where is this? Okay, where is this tuning fork when it's released the sound of the frequency of 485 hertz? Okay, so first, let's start with the Doppler effect calculation first. The observed frequency is, remember, we take the ratio with respect to the source frequency, and this ratio is the speed of sound, and we're going to deal with the speed of observer, speed of sound. We're going to deal with the speed of the source. Yeah. But this one is simpler in the sense that because observer doesn't move, so you can just can't take that away. And everyone knows when the source is moving away, the frequency will drop. So what you have is you just have to add these two numbers together. You want to lower, you want the bigger denominator to lower the observed frequency, right? This is a logic that we did in our lecture there. All right. And now your job is just substituting the numbers. The observed frequency is 485. The speed of sound is 340 over 340 plus speed of the tuning fork. And the source frequency is 512. There. Isn't that cool? In the sense that from this equation alone, you will be able to figure out what should be the speed of the tuning fork at this moment, right there. Nice. Okay, so once you have that, all you need to figure out is, okay, then use kinematic equation. Right. So what you need to use is, of course, the initial release point, the speed, initial speed, you might use U for that, is 0 meter per second. The final speed of your calculation is the speed of the source, which is the one that you just got. The acceleration over there is definitely G, 9.8 meter per second. What you want to figure out the displacement, right? You want to know what is the displacement of this object right there. So which sort of like relationship should you use? You say, well, John, I remember we can use V squared equal to U squared minus 2AS. So that will lead you to V squared equal to 0 minus or plus, in this case, because you can say down is positive, 2G and X. So that means X is just square root V over 2G. And you just take the V that you got from here, plug it in there, and then you are pretty much done.
Okay.
Does that make sense? Is it good? All right. So the first step, pretty much you use the Doppler effect to do the calculations. And then once you use the Doppler effects to figure out, hey, to generate the frequency of surf of 485, the tuning fork must be traveling at the v sub s speed. And then you use that speed to be your terminal speed in your kinematic calculation. Yeah. You drop something down from the 0 meter per second speed. How long does it take for the speed to reach v sub s? Under gravity, 9.8 meter per second. You're done. Is it good? Okay. I think this is it's a kind of nice question that's, you know, university college physics, university textbook love to ask, because it combines the kinematic calculations along with the, you know, Doppler effect and, you know, things like that. So this is the thing. But I mean, yeah, I think this is the level of the exam question. I think it's not too far off. A little bit of time should be able to, you know, get you to be able to solve this one. I hope. All right. All right. Question 12. Yes, definitely. Okay, so this one's good. Yeah, I can slide up. Okay. Okay, so let's do homework 6, question 12. There you go. If a human ear canal can be thought of as resembling an organ pipe, right, closed at one end. So you can think of your ear canal to be this type of air columns. Okay, one closed, one open. And let's say that resonates, right? Every time you talk about resonates, means you're generating standing waves. It resonates at a fundamental frequency of 3000 hertz. You guys still remember the fundamental, right? When you say fundamentals, mean you can fit the simplest kind of the waves in this air column here, which is mean it's going to be the lowest frequency or the longest wavelength right there. And the information said this fundamental frequency, I can put the 0 or the not symbol on it, just say this is your fundamental frequency is 3000 hertz. There you go. All right, what is the length of the canal? As simple as that. So this one just to warm things up. I just want to make sure that you have a chance to solve this kind of like, you know, question in the standing wave in air columns and things. So over here, they say it takes the speed of sound in the air to be 340 meter per second. So from here, that means that allow you to calculate the wavelength already. So the wavelength is just the speed over frequency. You guys with me? You have V equal to F lambda. So the lambda is V over F. So it's going to be V over VF naught. And that is going to be 340 over 3000 in meter. But then now go back to our conditions over here. What you have over there is just its fundamental frequency. So that means what you have over here, this is the length of the canal. But you guys know as well, this is just half a loop. Or if you don't like the loop thing, okay, if the loop, imagine like this is the whole loop, right? Oh, this is too thick. Wait a second. Here, this is the whole loop, right? All right. And what you're looking at is just half a loop. And if you don't like the concept of the loop, that is fine. You can think of this one is just like, well, John, what you're doing over here, this is just a quarter of a wavelength, half a loop. And that means you can just take this to be the length of the tube. Okay, so that means what you have over here is lambda is 4 times the length of the tube. You just take that 4 times the length of the tube there, and that allow you to figure out what should be the length of the tube. It's going to be 340 divided by 30,000, 3,000, sorry, and then divided by 4. And that's it. You are done.
Okay.
Okay. So this one is the one that just want to test that, hey, you know, the relationship between figuring out the wavelength in the tube and the length of the tube itself. And then you know that fundamental frequency, what does it mean? Or if you want to go to the different harmonics or different overtones, then you should be able to link or connect between the size of the wavelengths that fit in that tube or in that air column there. Okay, very nice. Okay. You might say this is maybe too simple for the exam, yeah, maybe. And 14 and 13 and 14. All right, we'll do everything. All right, we'll just complete this one. All right, good. We should do that, right? Because Ajahn just said that this is too easy for the exam, so there must be some more complicated question. Okay, guys. 13. So you have fundamental frequency of an open organ pipe corresponds to the middle C, which is about 261.6 hertz, all right, on chromatic musical scale. All right, so this is just the standard C. So what you have over here is the third resonance. Now they want the third resonance of a closed organ pipe has the same frequency. What is the length of the open pipe, or in the case of B, the closed pipe? Wow. All right, this is good. This is question that could show up in the exam. This is somewhere, I mean, you need a little bit of analysis there. Okay, so let's draw some figures, shall we? So first, they talk about the open pipe. So it's gonna be open, yeah, like that. Okay, and they say fundamental. This one give the fundamental of the middle C. So that means if you say fundamental, it's gonna go like this, right? Because it's an open pipe. Oh, sorry, it's because it's an open pipe. So it means both ends gonna be antinode, and the node is gonna comes in between. So what you know from this is, of course, this is exactly one loop or half a wavelength. So it's one loop or half a wavelength is equal to the length of the tube right there. Cool. All right. So with this, that means the lambda is, okay, let me write on the side here. Lambda is 2L. And the frequency is just V over lambda. It's going to be V over 2L. And this is your fundamental frequency. And the problem gave you that this is 261.6 hertz. There you go. Okay. So that means from here, you should be able to calculate the length of the pipe already. Yeah. Okay, cool. So this one, I think I forgot to put, but I mean, usually you can take the speed of sound to be 340 as usual. So from here, this right there, you can take it to be 340. So that means, say, the length of the tube is just 340 divided by 2 to 61.6 hertz meter per second. Here we go. There. Okay, so this one just testing your, once again, one more time, how to relate the type of the standing wave with the air column. And this one, the key one is it's a fundamental. All right, now the more challenging one is part B. Part B says, now you have a closed pipe, whatever that is. All right, it doesn't have to be the same length, right? Just different length. And let me call this L prime, then it's different pipe now. It's one closed and one open. And it says you get the same frequency, but it's at the third resonance. So it is third, right? So when you talk about resonance, the idea is the fundamental will be your first, because we already discussed briefly about the wording, the terminology. When you talk about resonance, that means you can create standing wave. All right, and we already saw that there are so many types of standing waves, starting from fundamental. You go to the first overtone, second overtone, or you can talk about harmonics. Depends on the type of the pipe. Okay, so it's a multiple of frequency from the fundamental. So the idea of this one is a third resonance. So when you say the third resonance, mean it's going to be the third types or third possibility counted from the fundamental. Does that make sense? All right, so let me write it in full over here so you can compare, contrast. Here we go. So if I want to list all the resonance possible, So the first resonance will be the one that we just did in the previous example. That's your first resonance. And the second one, you put one more twist to it. That's your second resonance. And then the third one, you're just going to have to add one more twist to it. There you go. So does that make sense? All right. So just to recap, you're going to call the second one here is the first overtone. And you're going to call the third one to be your second overtone. But I mean, this one is just, this problem just speak loosely saying that, hey, the third resonance. Okay. So this is your third resonance. Okay, does that make sense? All right, just all right. First resonance is your fundamental. Second resonance is your first overtone. Third resonance is your second overtone. Okay, let me write on the side here. It's the second overtone. There you go. All right, cool. Now, the job is kind of done in the sense that now all you need to do is just count. If you want, that is one loop, two loop, and a half. Okay. Or if you don't want to do the loop thing, you can just say, but John, this is that's one complete wavelength and a quarter. So that means what you have over here is you can see now your length of the tube, the L prime, is 1 plus a quarter of a wavelength, or 5/4 lambda. You guys with me? Okay. All right. So if you want to go from the starting point, so this is going to be L prime equal to lambda over 4. This one's going to be L prime equal to 3 lambda over 4. And the third one is going to be L prime equal to 5 lambda over 4. And with this, now you can calculate the frequency. Once again, it's going to be V over lambda. It's going to be V over 5 lambda over 4. Just flip it over. Okay. All right. And that's it, guys. You will be able to figure out what should be the length of the tube right there. So, what I'm writing over here. So actually, I would love to write this one as the lambda is 4L prime over 5. So I should actually substitute that one in more than just taking the wavelength there. So it's V over lambda. And the lambda is just, okay, wait. Okay, V over lambda. So it's a V over 4L prime. I flip 5 to the top. There you go. And from here, you will be able to figure out the L prime. With me, guys? All right. Cool. Okay. Does this help? I hope this works a little bit. Very good. All right. If there's no further questions, let's move on to 14, shall we? All right. Go 14. Homework number 6, question 14. All right. Now you have a tuning fork with the frequency given of 512 hertz placed near the top of the tube shown in the figure. The water level is lower so that the length L slowly increases from the initial value of 20 centimeters. All right, the water is increasing. It's not. Is it increasing or decreasing? It's lower. Okay, the water level is lower. It's supposed to go down. Determine the next two value of L that correspond to resonance modes. All right, so they just want 2 more resonance when the air column is actually get longer. Okay, so this is kind of like nice question because it gives you a contrast of the problem. What you had here, the length of the air column is fixed. You only adjust or you are considering the difference value of the wavelengths that can be put inside that fixed length air column. But over here, we just, turn our problems around, saying that, hey, I have a tuning fork generating the frequency, which is fixed, 512 hertz. That's it. So it means in this case, the wavelength is fixed, right? And now they say, hey, when whatever the level of the water is, okay, I don't know, here, so you have the length over there, L. Somehow they say you already have a resonance. Yeah. They said the initial value is 20 centimeter. So initially, so let me put this, not over here is 20 centimeter. This is where you already hear the loud sound somehow. Oh, it doesn't have to be. All right, it just lower from 20. Okay, so who cares? All right, let's just keep lowering down. So determine the next two values of the L that correspond to the resonance mode. All right, so it might not be fitting anything. So what we can do right now, first things first, I think it will be clearer if you're still confused what I'm explaining. Let me find out what is the wavelength of the sound right now generated from this tuning fork, shall we? All right, so that means the wavelength is going to be speed over frequency. And we can take the speed of sound to be the same number, 340, if you want, meter per second. The frequency is 512. So this is already the wavelength. All right. And just because I think we really need this one, I think I'm going to punch the calculator here. 340 divided by 512. Here we go. And it's 0.66. 4. I mean, I don't know, do I need the third digit there? But anyway, that's what it is. So that's the wavelength. Or if I want to work in terms of the meter, is centimeter, it's going to be 66.4 centimeter. That's the wavelength of the sound generated. Cool? But then now look at the air column over here. You start with the air column of 20 centimeter. All right, now it's the font right here. If you start from the fundamental needs exactly this. Does that make sense? Okay, it might not be, but at least the point is the fundamental need lambda over 4 to start the standing wave at the fundamental, I mean, the first time, let's say. The length of the air column that eventually give you a resonance will be when the length of the air column is half, a quarter of a wavelength. You guys with me with this? Okay. So what you have here is lambda over 4 is going to be, all right, I'll take 4 divided. So it's going to be 166. So this is it. So when the water level is down from the top of the tube to be at 16.6, you will hear the loud sound coming out of the air column. However, your starting point is already starting at 20 centimeters. So you're already far away from that 16.6. So you already passed your fundamental frequency. I mean, the fundamental resonance sound setting. Does that make sense? So you would expect the next possible to have a loud sound coming out is when you're going to have this here. So you just have to add an extra half the wavelength into this length of the air column. You guys with me with this? Okay, so the next time that you are going to hear loud sound from this air column is when the air column length is lambda and a half plus lambda over 4, which is 3 lambda over 4. You guys with me to this, yeah? So this is where you're going to hear the next loud sound or next resonance mode is going to be 3 lambda over 4. And of course, you can keep lowering down the water level. You're going to have to add extra lambda and a half, another loop, for you to be able to hear the next loud sound. And that will be when it's reached 5 lambda over 4 down here. Does that make sense now? I hope. Okay, let me draw the air column down here. Here we go. Okay. So you can just take the numbers right here. So the answer will be the resonance mode. Resonance modes are at the L equal to 3 lambda over 4 and 5 lambda over 4. And you are done.
Okay.
Cool. So this one is already passed. Okay, you're starting the air column level at 20 centimeters. So you already passed the first possible resonance mode. You have to lower the waters down until the air column hits the length of 3 lambda over 4. That's when you hear one next resonance mode. And then you keep lowering the water level down further until you hit 5 lambda over 4. You have another loud sound coming out. And then you can keep lowering it down more and more if you want. Yeah, up to the size of that tube, glass tube there in the problem. Okay, does this help? I think by going through these 3 problems, I think is a good revise on the subjects over here about the standing waves. Good picks. It's like you picked everything actually. Very nice. Cool. All right. I think good shape. Can we see? Yeah, definitely. So let's move on to homework 7. So I think that's kind of nice too, because it seems like we have gone through the homework set 6. Yeah. So now we can move on to 7. So let me pull that up. There you go. All right. Problem number 7 and 8. Okay. Those 2 at the end. It's about lens. Okay. Very good. So let's do that. So what you have is, once again, the homework 7, question number 7. Okay, there you go. All right, now you have a thin lens, has a focal length of 25 centimeter. Locate and describe the image when the object is placed. So this is like a testing the utilization of that lens equation, on and on. So oh, that's a question. It doesn't say what type of lens is this. All right, but by looking at this, and it said the focal length of 25. Well, it's positive though, right? So we can take to be converging lens. Okay, this is maybe my bad. I didn't specify what types of lens is this. Okay, that's fine. So let's assume, let's say, take the focal length to be 25 positive centimeter. There you go. All right, so we assume that it's a converging lens. All right, so part A is when the object location is positive 26, right? We already said it's always positive when you have only a single object there. So it's definitely going to be in the front. So you use 1 over P plus 1 over Q equal to 1 over F. And then what you want to figure out is what is the Q, the image, location, and type. So it's going to go somewhere like this. And you can just substitute it in 125 minus 1 over 26. So that means your number will look like 1 over 25 times 26. You guys with me so far? All right. And that means the Q that you get at the end is 25 times 26 centimeter. And it's still positive. With me?
Okay.
All right. So what does the positive image location means? It means this is real image. Cool. Because it's positive. When the image location is positive, means everything is real. And that means the image will show up after the lens. So if I want to draw like a diagram over here, it will look something like this. F is positive 25 centimeter. Okay. 25 is here, 25. That's 25. And then you place an object just shy of that 25. It's 26. Okay. Just a little bit to the left of that. So what is this? It means your image will show up so far away. It's huge number. All right. But anyway, it's super far, but it's positive. So the image will show up behind the lens. So they want the magnification. So let's do the magnification. The magnification is negative Q over P. So it's going to be negative Q 25 times 26, already taken care of the sign, over the P equal to 26. They're both positive. So let me put positive sign on both. All right, 26 cancel, bam, bam. You get negative 25. So what does it mean? It means the image is inverted. Inverted. And it's 20x magnified. It's multiplied by 25 times. So this means the image will be so far away, 600 something centimeter. And then it's going to be 25 times huge. It's like, I don't know where, upside down. You see what I'm saying here? It's going to be inverted 25 times larger. And it's real. Okay. Cool. Oh, wait. Oh, I think I see it. My bad, guys. It's my bad. Forget about this. I read completely wrong. My bad. Sorry, I saw it already now. It's in front of the lens. Oh, that's right. Oh, my bad again. I think this is good. Sorry. Oh, that was number 8. I'm confused. Are we doing number 8? 7. Okay, sorry, my bad. Okay. The object is placed in front of the lens. Okay, good. I thought like the image was 26 meters in front of the lens. Okay, sorry, my bad. Okay, this is good already. It's done. All right, didn't get good sleep there. All right, so this is better. All right, this is how it's done. Okay, let's do it one more time, part B. So for part B, you pretty much follow the same step, except now you use P equal to 24. So that means it's just a little bit, closer here. So part B, okay, let me write another one here. So for part B, the lens is here, the focal length is there, and then now you place your object just shy of that focal point, 24. So this is 24. All right. So what you have, you do the same thing. 1 over Q equal to 1 over F minus 1 over P. All right. I'm just skip one step right there. And it is 1 over 25 minus 1 over 24. Now, as you can see, now it's negative 1 over 24 times 25. So your final value of the Q will be negative now. See? So what does it mean? It means now the image is virtual and it's appear in front. Yeah. The reason it appears in front because of that negative sign right there. So let me write nicely here. There you go. It's virtual. When you say you have a virtual image, it must appear in the front. So you want to know exactly what shape and, it's inverted or upright. You say magnification is negative Q over P. So it's going to be negative of the negative 24 times 25 divided by P, which is positive 24. 24 cancel. You get positive 25. So what does it mean? It means it's upright. But now it's 25 times 25x. So that means when it crosses the focal length in the front by just a bit, you generate, this is not in scale, but it's huge, like 25 times, okay, upright, because this is 25, so it's upright, and it's 25 times bigger, and it's going to be virtual. That means it still stays in the same side of the object. This is the magnifying glass. Think of it that way. Okay, when you place your magnifying glass in front of the letter will appear larger. But this one is huge. It's like 25 times larger. Okay. Very nice. Cool. All right. So I think this is a good review of the either mirror or lens equation, right? They use the same form. 1 over P plus 1 over Q equal to 1 over F. Nice. Okay, let's do one more. Homework 7, number 8. All right, so let me zoom back in here. Okay, homework 7, question 8. There you go. An object located 32 centimeter in front of a lens, okay? And forms an image on a screen. Wow, when you have an image that can be formed on a screen, it must be real. Behind the lens, that's good because the real stuff goes behind the lens. Find the focal length of the lens, determine the magnification, and its lens converging or diverging. Right? I think I can guess right away it's going to be converging. Right? That mathematics takes care of everything here. You have a lens that you don't know what type it is. Okay, let me put it here. That's the lens. It could be whatever. Let me put it there. All right. And object is 32 centimeter in the front. So it's right there, 32 centimeter. And the image is being formed 8 centimeter. It's pretty close. It's 1/4 of that. So that is, here we go, 8 centimeter image. So what you have over here is, it means the P is 32 centimeter. The Q is positive 8. You guys with me with the sign? Okay, I think just to be clear, it's positive 32 centimeter for the object distance. And the image distance is positive 8 because it's real, it's appear behind the lens. Everything is positive for the image there. So from here, you can calculate the focal length right away. It's 1 over P plus 1 over Q. And then you can see it's definitely is going to be positive. It's 5 over 32. So that means your focal length is positive 32 over 5. When you say it's positive, (32/5), that means this is a diverging lens. With me? Okay. What is the magnification? The magnification is negative Q over P, and that means it's going to be negative Q, positive, right, over P, positive 32, is negative 1/4. So it means its reduction in size. It's going to be 4 times smaller, and it's upside down, which is fine. You have an object here. At the end, you get image here, 4 times, I mean, just 1/4 of the size, and it's inverted upside down. And the lens is converging. You are pretty much done.
Okay.
So I hope one more time, I think the question about the lens equation and everything, it's going to be quite all right because we have done, I think maybe the most complicated one already in the extra handout. If you remember that extra lecture there, that we have question regarding you even mix the mirror and lens together, right? But I mean, the one that's complicated just all right is when you have the composite system, right? When you have 2 lens system in microscope or in telescope, you have the first lens and the image from the first lens being treated as an object for the second lens, and then you find the final image. That will be, I think that's already good in terms of you already know how to apply mirror equations, lens equation in that type. I think that's very good already. Very nice. Cool. All right. Oh, if you come this far, then that's already, that's the last topic that we are going to cover in the second exam. Nice. Okay, just let me know if you have further question. It's like you only the one who asked question. Oh no, not really. Oh yeah, you are. All right, very good. Thank you for that. Nice. That's all from me. Okay, welcome. Very good. I hope this helps a little bit, at least give you something. But I think your friends will appreciate that. We think maybe it's the same questions. Yeah. All right, guys. Okay, feel free to ask more questions. And if you're done, then all right, take care. I'll see you. Maybe not seeing face to face, but the exam will be tomorrow. Okay. All right. Any of you here that cannot make it to tomorrow's exam and want to do the Monday session instead? Not here. All right. So everyone can do tomorrow. Okay. All right. Cool. Thank you. Okay. Let me stop recording for now. No questions.